Thank you, Puya, for the introductions. My name is Ling Zhao. I'm a structural engineer working for Microbaker Joint Corporation located in Hamilton, New Jersey. Today I'm going to talk about the bridge structural response spectrum analysis and seismic design. Obviously, and this is a big topic with a lot of subject materials. So my presentation mostly will be in the conceptual level. I'm talking about a lot of materials, so I will go through the slides very quickly. I have about 60 slides. Okay, let's get started. Recently, there has been a trend for the seismic design of bridges migrating from force-based design based on the Untitled ARP code to the displacement-based design based on the Untitled guide spec for seismic design. And this has generated some needs for this training. So I'm going to talk about some of my experience here as regard to using the Untitled guide spec with displacement design method for doing the seismic design. So, just 1 second. All right. The outline of my presentation will be first I'm going to talk about the definition of response spectrums. Then I will discuss the multimodal response spectrum analysis, and then about the mass and stiffness and damping modeling, and some bridge modeling issues, and then the concept of displacement-based seismic design, and then give you some examples of my previous design. So the definition of response spectrums, if you take a classic dynamic single degree of freedom equation motions as written here, and mx double dot plus c x dot plus kx equal to minus m times xg double dot. And this equation motion can be written as seen here, x double dot plus 2 cos omega times cos double dot plus omega square times x equal to minus xg double dot. And the solution of this classical single degree of freedom equation motion is through the Duhamel integrals. So you got the Duhamel integrals, and you can get the time history of the single degree of freedom response, displacement, velocity, and the acceleration response for the system. Now, as an engineer, we're not interested of the whole time history of the response, but we're interested on the maximum, the peak response quantities of those acceleration, velocity, and displacement. So we're only going to take the maximum over the time history of the xt to get the peak response. If you follow the mathematics rigorously with assumption of a small damping ratio c, you can get a relationship between the peak response of the velocity and the acceleration, as the velocity, peak response velocity is equal to omega times the peak responsibility of displacement, and the peak response of acceleration is equal to omega squared times the peak response of displacement. So a response spectrum is defined as a plots of a peak response quantity, means the peak response of a displacement, velocity, and acceleration of a single degree of freedom system subject to the given ground motions, versus the horizontal axis which will be the fundamental period of the structure, the SDF system, T. And also I need to mention that the response spectrum is also a function of a damping ratio per C. Usually we use a 5% critical damping as our design basis. So for a range of a possible earthquake at the site, the design response spectrum is defined as you construct a response spectrum for every single xg the equation ground motions, and you construct the spectrum for all of them, and with each ordinate have a uniform probability of existence. For example, 7% probability of existence in 75 years, which means 100 years return period, over all period, and that will give you the response spectrum we need. But practically we're doing usually we're doing a smoothed response spectrum constructed by 3-point method. So so the generic design response spectrum constructing using 3-point method is first get the peak ground accelerations, then the SDS, which is the 2.2 second response spectrum spectral accelerations, and then get the SD1, which is the 1 second period spectral accelerations. Once you have those 3 points, the first segment is from is a linear portions going up from the PGA to the SDS, and then from the T0 to TS, it's a plateau sections. It's a constant equal to constant SDS, and then starting from TS going out, and then it's the spectral acceleration is just equal to SD1 divided by T. And this generic design spectrum is associated with 5% critical dampings. And the definition of a generic design spectrum is really it's really easy. You can actually get your response spectrum online. Just first, you need to get your latitude and longitude of your project locations, and then find your site classification. Either you are on site class A, B, C, D, E, F. There's 6 site classes, and define your site classes, and then just go to this USGS website. This link here. You can go to this website and input your latitude, longitude. You can even input your code, and then input the site classification, and the website will spit out the response spectrum for you immediately. So let's try that here. Try one. Let's see. Hold on, just 1 second. Okay. Let's see if it works. Okay, if I go to. Let's see if I go to this website. Let's say this is a USGS website. Please select the code. I would say 2009 Ashto as the hazard data, and then report type also test, and say site soil classifications. I say site class D, which is steep soil. Now the latitude and longitude. Let's see what I'm having here right now is okay. Let's go to sorry. Okay, you can actually find your longitude and longitude of your section of your project location by go to the iTouch map. So you can see here, and then iTouch map. Let's see latitude, longitude. So I'm going to type in the address, my address here. Okay. So I'm typing that address and say go. And here it spits out the latitude and longitude for you at this location. So I just copy that. I copy that latitude into this website here. Oops. Sorry. Control C, Control V, and then I copy this longitude into my into the SGS website, and I just say compute values. Now the website is going to spit out the report for you, which shows up right here. So I'm sorry, which is here. Okay. Now you can ask them to give you a detailed report, or you can ask them to give you a generic report. And this here is the generic report. They give you the PGA the short period spectral accelerations, and S1 is 1 period, 1 second acceleration. You can also ask the website to give you a detailed report. It's a view detail report. And this report here basically tells you how this response spectra is being constructed. It gives you the PGA, the SS, and S1, and then talk about the site classifications, what for site class D, and then give you all the factors here, and then give you the constructed response spectrum based on the 2009 Untitled guide spec. So this is very convenient tools for generic design spectrum. It really is just a mouse click to get those. So let's get back to our presentations. Now, once you got your response spectrums, the next step you need to do is you define your seismic design category. Right now, in the 2009 Untitled guide specification for LRFD seismic design, and then divide the seismic design category into 4 categories, depending on your SD1, the 1 second spectral acceleration, and divide them into A, B, C, D. As the alphabetic number goes up, and then the seismic intensity also goes up. And based on the seismic design category, the code asks you for different flow chart. As you can see, for seismic design category A, which is very light, basically no seismic hazard area, you don't need to do anything. Just follow the minimum requirements and you'll be done. For seismic design category B, you need to do a demand calculations. You don't have to identify your earthquake resistance system. You can calculate your displacement capacity per the implicit capacity equations and check whether the overC is less than 1 and be done. And then SDCC and SDCD, they ask you to require you to identify your lateral force, lateral load path. What is your load path to resist the seismic loads? And you need to do a demand analysis, and you also need to do pushover analysis to come up with your displacement capacity. Of course, you also need to do the detailings. In terms of the analysis procedures, the 2009 Untitled guide spec does not require you to do anything for seismic design category A, but for seismic category design B, C, and D, you need to do your demand calculation per either using the equivalent static analysis, which is what we call the uniform load method, or the elastic dynamic analysis, which is essentially response spectrum analysis. Now, the Untitled guide spec does not require you to do nonlinear time history unless the P delta effect is too large to be neglected. If you have a P delta effect in your structure, it cannot be neglected. Or the damping provided by the base isolation system is too large, or it is required by the owner. So the response spectrum analysis, the elastic dynamic analysis, is the major tool for your demand calculations. So let's go to talk about the multi-mode response spectrum analysis. As you learn from your structural dynamics basics, response spectrum analysis, the governing equation for multiple degree of freedom system is written by this equation here. You got your mass matrix, your damping matrix, stiffening matrix, and this R here is the ground motion influence coefficient. Means when you have the earthquake comes in the horizontal X direction, let's see, and it's going to excite all the degree of freedom in your structure system in the X direction only. So that R coefficient, that R vectors describe such an influence coefficient. Now, before you can solve the response spectrum analysis, you have to do eigenvalue analysis. The eigenvalue analysis will give you the fundamental period of your structures, and also the eigenvector matrix, the load shape, basically eigenvector matrices. Once you have those eigenvector matrices, you can left multiply the eigenvector matrices to your system using x equal to phi times q, and left multiply phi transpose, and you end up with the equation on the bottom here. Sorry. end up the equation within the bottom here. Because the eigenvector is orthogonal with regard to the mass and the stiffness, so the multimodal response, that governing equation can be decoupled into a series of single degree of freedom equation motions, which is written here. Qi double dot plus 2 cosI omega I times Qi dot dot plus omega I square times Qi equal to minus gamma I xg double dot. Now, if you look at these equations, it's essentially the same format as a single degree of freedom. So you had the response quantity instead of x, you got a q, and the cosI is the modal damping ratio of this mode that you were considering, and omega I is the circular frequency of the ith mode that you were considering. And pay attention to this gamma I here. This gamma I, which is given by phi I transpose times m times r divided by phi I t times m times phi I. And this gamma factor is what we call the modal participation coefficient. This gamma factor basically describes how significantly this mode, the ith mode, is being participating on the ground shaking. And you can view this single degree of freedom equation as a this governing equation here as for every mode. It's just the equation motion for each mode, essentially SDF equation with the ground motion being scaled by a factor gamma I. So you just have a bunch of a single degree of freedom system, and the ground motion is just being scaled by a gamma I, which is associated with each mode. So with that in mind, for solving your multimode response spectrum analysis, it becomes simple. You just use your the ith mode period Ti and the modal damping ratio cosI, and read the response spectral acceleration SA from your design response spectrum, and then you use that SI and times this gamma I, because response spectrum analysis is linear. When you scale your input by a gamma factors, you're going to get an output scaled by a gamma factors. So basically, the Qi is going to be a gamma I times SAI. Remember, the Qi is the non-dimensional quantity, and the displacement is just equal to the phi, the mode shape times this Q. So your responsive accelerations, you can get it as your gamma I times SAI times the mode shape ordinates. And the responsive velocity, you got this relationship divided by omega I, and the displacement is divided by omega I square. So that way you get this response acceleration, velocity, and displacement for each mode. And theoretically, we don't need to consider. We need to consider every mode, but we don't want to do that because there's too many modes. So we need to cut off. We need to cut off the certain modes. So the principle for cutting off the modes is what we call the mass participation. What the code asks you to do is you need to consider at least 90% of the total mass to be participated in the ground shaking. So let's look at the base shear here. The base shear from the ith mode, Vi, is equal to the summation of the mass of each degree of freedom times the response acceleration of that degree of freedom, and you sum them up. So you follow the mass and use the replace R response acceleration by gamma I times SAI times VGI, and then taking the gamma I times SAI out of the summations, and then replace this sigma mj times VGI in matrix form, which can be written by these three variables here. And remember the gamma I is equal to gamma I, the modal coefficient, modal participation coefficient is written by this formula here. If you look at the Vi and gamma I here, and basically it's the Vi can be rewritten equal to gamma I square divided by phi I t times m times phi I times SAI. Now, if you have a mass normalized eigenvector matrices, the Vi will just simply equal to gamma I square times the SAI. So the gamma I square here is like a mass to you because mass times the acceleration is equal to the base shear. So the base shear from the ice mode is basically the gamma I square times SAI, and this gamma I square factors describes the mass participation. So when you cut off your modes, you just need to make sure that the summation of the gamma I for all the modes that you have selected is larger than 90% of the total mass in the system. Almost all the every finite element program now has described the mass participations. Midas has a table that can give you the mass participation for every mode, and you can look at them. But the bottom line is you need to have 90% in each direction in your system when you cut off your modes. So once you get the modal response for each modal maxima, Ri, you need to combine them into your to combine the result from different modes. This is what we call the modal superpositions. And the combination of the modal maxima, there's three major methods right now. First is the absolute maximum, which is you just add up the maximum value from each mode, the absolute value of them up together. And this way is too conservative. And then the next one is the called SRSS, is square root of sum of square. And this modal combination here is based on the assumption of a totally independent response. It means each mode is independent of each other. So you can, based on the random process principle, you can use the SRSS to combine them. But this SRSS has some problem when you have a modes. When you have two modes which is very close to each other. For example, one mode you got a fundamental period of 1.1 second, and the second mode you got a fundamental period of 1.2 second. You know, the fundamental period of these two modes, they're so close, so it's hard to say which mode is. Hard to say that these two modes they're not affecting each other. So in those cases, your SRS result is going to give you erroneous result. So the required method by the AASHTO right now is the CQC, what they call the complete quadratic combinations. You need to use this cross-modal coefficient calculated by this formula here, and then basically use this formula to calculate response. And what the CQC does is going to, if you have two modes, if your Ti over Tj becomes close to 1, the CQC goes back to absolute maximum combinations. When the Ti over Tj is very far away, it's almost similar. It's almost identical as to the SRSS combinations. So CQC is what is being required by the AASHTO. Now, after you combine the modal, after you do the modal combination, you still need to do the directional combination. The earthquake happens in 3 directions: in the horizontal X, horizontal Y, and in vertical directions. So you need to combine the different directions together. The principle behind this combination is that the two principal direction earthquake, the X and Y direction, they are totally independent from each other. So the SRSS rules can apply. If you do the SRSS rules, it has been proved that it's basically within 5% of those the result obtained from the commonly used 30% rule, means which is given by the second bullet here. You just use a response from one principal direction plus 30% of the absolute value from this secondary horizontal directions. Now, regarding to the vertical response, generally you do not need to include the vertical response in your direction combinations, and actually also does not require you to combine the vertical direction response to your horizontal direction response. And the reason behind that is the vertical response is generated by the P waves, and the horizontal response is generated by the SH waves. These two seismic waves, they come in different times. So the maximum intensity of the earthquake in the vertical direction and the horizontal direction, they occurs at different time. And so you do not need to consider, you do not need to combine them. However, in this regard, some DOT may have different requirements, and some DOT has been required that you need to consider 30% of the vertical response combined to your horizontal response as well. So you just need to combine and comply with the code standard you're being designing to. Now, so we go to the mass stiffness and damping modeling. So for response spectrum analysis, when you build your model, modeling means just to build a mathematical representation of the mass stiffness and damping matrices in your object structures. So first talk about mass. Let's talk about mass modeling. The criteria for the mass modeling is all the components in your system that will create inertial forces needs to be modeled. And this gives the question that we really have regarding the foundation mass. Do we need to consider the foundation mass in the model? Do we need to consider the pile cap mass? Do we need to consider the pile mass in the model? The answer to that question is, per this criteria 1 here, is that every component that creates inertial forces needs to be modeled. If you have a rigid foundation type, your foundation mass is like a rigid attachment to your foundation, so that means there will be no relative displacement between the foundation mass and the ground. So there will be no inertial force generated from the foundation mass, so you do not need to model those foundation masses. However, if you have a foundation flexibility, there will be relative displacements, therefore there will be relative accelerations from the foundation mass to the ground. Therefore, there will be inertial forces associated with the foundation mass. Therefore, you need to model those foundation mass. The foundation mass, the mass modeling includes not only the translational mass, but also includes the mass moment inertia. This can be a problem when you have the span models, when you lump all your mass to a line, and you might lose your mass moment inertias. So those things need to be considered when you're modeling your mass. And then let's talk about the stiffness modeling. For stiffness modeling, for all the components that is not expected to yield, we use a linear elastic stiffness. For example, the superstructure, we don't expect them to yield. Precious concrete, conventional bearing, foundation, we don't expect them to yield, so we model them using linear elastic stiffness. For cracked reinforced concrete, we use effective stiffness. The effective stiffness of reinforced concrete, cracked reinforced concrete, is given by the my divided by phi y, where the my and phi y represent the yield moment and curvature for bilinear moment curvature approximations. I'll talk about what that means. So, if you do a moment curvature analysis of your reinforced concrete columns, it's going to be giving you a curve like this, this solid line here. So the moment curvature curve is a plot of a moment versus the curvature, the moment on the sections plus the curvature on the sections. Because as you can see, this is a very nonlinear sections, and the bilinear approximations give you approximate this actual moment curvature curve by a perfect elastic plastic curve. And the EIE, the effective stiffness that you should use in your model, is what this green line depicts here. green line, which means the elastic response line, and that's the stiffness you should use in your model for your reinforced concrete column. Instead of doing the explicit movement curvature analysis, the 2009 ASHTO guide specification already gave you the EIE over EIG ratios, which is given by these two figures here. The top figure is for the circular section, and the bottom figure is for rectangular sections. Obviously, your moment curvature curve will be dependent on your reinforcement ratio and your actual load levels. So there's a different curves for different reinforcement level and different actual load ratios. You, instead of doing a moment curvature analysis, you can just pick your points based on your design sections, based on the actual load expected in your column. Just a pick point from this curve and use those as your effective stiffness. Now, for the modeling of damping, damping is a very complex problem, so it's really hard to capture them in the model because, in other words, our structural damping usually comes from the hysteresis damping. Like in this loop showing here, it's a nonlinear response of your electrical resistance system. It's a nonlinear response, in each loop, on every loops, is going to take away some energy from the system. And so that energy taken away per each cycle is what we call the AH, the energy dissipation per cycle. And then the strain energy of your system at the beginning of the cycle is called AE. And this is a hysteresis damping system. And what we have for our classic structural dynamic governing equations, what we have is a viscous damping. And the hysteresis damping does not equal to viscous damping. So we need to find the equivalent viscous damping, which is given by this equation here. And here is some background of how this equation comes from. Basically, it's just a first order approximation of a Taylor series expansions. By the way, this is a conservative assumption here, and realistically, when you have a Cassie equivalent here, for example, now for the case that when you have the AH equal to AE, let's say, the energy dissipated per cycle is equal to the strain energy at the start of the cycle. Theoretically, you should not get any vibration anymore, because that's the case what we call the critical damping. So there will be no vibrations. So theoretically, the Cassie equivalent for that case should be equal to 1. If your AH equal to AV, AH equal to AE, you should got 1. But in this case here, what you got is 1 over 4 pi. Is about 7%. So this equation is a approximation, is a conservative approximation of your hysteresis damping. Instead of going through all those damping calculations, usually people just assumed for steel structures it's recommended to be 2 to 5%. For concrete structure, recommended to be 2 to 7%. The common assumption is 5%, and it's really hard to argue with that 5% assumptions. And that's become what we need to do. So what the code is the response spectrum recommended by the code is based on 5% critical dampings. In the 2009 ASHTO guide specification code, there is a damping reduction factor, which is given by this formula here. You can take advantage of these damping reduction factors if you're sure that you have damping in your system more than 5%. So the maximum you can go is 10%, which will give you some advantage of 25% saving on your response accelerations. But the code says if you want to consider critical damping larger than 5%, you need to have this condition met. First, there's a substantial energy dissipation through soil at the abutment. Second, there's a special energy absorption device employed. And then third, predominantly the structure responded as a single degree of freedom system. Now, if you're sure you have those damping reduction you have a damping larger than 5%, you can take advantage of it and reduce your seismic response acceleration by maximum 25%. Now, let's go to the bridge modeling issues. To build a model, inclusion limit of the model, usually there's a global model, frame model, bent model. For global model is you model everything from abutment to abutment. And for frame model, you just model between movement joints. And for bent model, you neglect the superstructure, just model the substructures. Global model is rarely used. Frame model is most commonly used. And bent model usually is used for develop the effective bend stiffness, doing the moment curvature analysis, pushover analysis, etc. So modeling the superstructures, there's three methods of modeling superstructures: span model, grillage model, and prototype model. Span model, in span model, you basically dissolve your superstructure into one line. You're just following the center of gravity of your superstructures. That one line will become represent the overall superstructure section properties. And regarding to the mass, the superstructure mass moment, the superstructure mass, if you lump them into one line, you're going to lose the mass moment inertia of your superstructures. So you need to split the superstructure mass into two equal half mass and place them at RG away from the center of gravity. RG here is the radius of gyrations, and that way you can preserve your mass moment inertia for your superstructures. Then you can do grillage model. Grillage model is just following the centroid of your beam and connect them transversely by dummy members that represent the transverse stiffness of deck and diaphragms. And of course, there's a prototype model, which is exact member-to-member modeling. And for substructural modeling, it is member-to-member, and this is a very important modeling element. So you need to have those accurately in your model. And so moment curvature analysis and the pushover analysis can produce valuable information on substructural stiffness, displacement capacity, and ductility capacity. One thing I need to mention that the code asks you to say, for moment curvature analysis and pushover analysis, you need to use the expected, which is the average material property, instead of nominal, which have certain margins. So for concrete, the FC prime, FC expected, FCE prime is 130% of the FC prime. And for rebar, for 60%, for grade 60 rebar, the expected yielding point is 68 KSI. Now, for do your moment curvature analysis, you just need to divide your section into a series of stripes, and then you keep your plane section remain plane principles, and set two variables. One is the neutral axis. Where's the neutral axis from your? Where's the neutral axis? And the second is the phi factor, the curvature here. With these two variables, you can calculate your strain profile on every strip of your sections, and with the strain knowns, and you get your stress at each stripe from the stress-strain relationship. And this figure here describes the Mander's concrete stress-strain model. The blue line describes the confined concrete material constitutive relations, and the red line here describes the unconfined concrete material properties. The unconfined concrete is used for the cover concrete, and the confined concrete property is used for everything within the hoop or spiral. And the figure on the bottom here is the rebar stress-strain relationship, and this is based on all parts models. And you have a elastic phase and a plastic flow phase, and then there's a strain hardening phase. And those event points of those model can be found from the actual code. And so once you have those stress calculated, you just calculate equilibrium. You need to achieve the equilibrium in your sections, and you get a moment curvature curve. So this is a typical moment curvature curve calculated As you can see, the blue line, the solid line here represents the actual M-phi curve, and the dashed line here represents idealized perfect elastic plastic M-phi curve, what we call the bilinear moment curvature approximations. To construct the bilinear moment curvature approximation, you connect the 0, point to the point which represents your first rebar yield, and that becomes your response line, elastic response line, and then you adjust your MP, idealized MP, to have this equal areas, so that the area enveloped by the solid curve, by the actual M-phi curve, is the same as the area enveloped by the dashed curve, by the idealized curve. And that way you get your idealized perfect elastic M-phi curve. Now, once you got those M-phi curve, then you can just calculate your plastic hinge rotational capacity. And the equation is given by the plastic hinge rotational capacity is just equal to the, let's go back one here. Look at here, the phi u and the phi y. Phi u represent the ultimate curvature capacity of your section, and phi y represent the elastic at the point where your section becomes yielding. The plastic rotational capacity of a hinge is just equal to the phi u minus phi y times the LP times the plastic hinge length. And this plastic hinge length is given by the Asheville code right now. And for the reinforced concrete column, the LP is equal to 0.08 L plus 0.15 times FYE times DBL. And this basically assumes that within the analytical plastic hinge length LP, the curvature, the plastic curvature, the curvature is constant, so that you can calculate your rotational capacity of your plastic hinge. Now, let's do then once you know the plastic hinge property, you can start doing a pushover analysis. And for pushover analysis, it can be done with a simple hand calculation, in the method what we call the event scaling method. Let's look at this example here. Okay, we got a 1,500 kPa gravity loads acting on this two column bend here. And for the gravity loads, each column shares 750 kPa. And then you do a moment curvature analysis with that actual load, 750 kPa. You got this parameter here, phi y, phi u, the yielding moment, the plastic moment, and the effective EI. And then you use that MYI here, 3549, and because there's a hinge here, and there's well, the boundary condition of the column at the bottom column is assumed to be hinged. Now you have two hinges at point B and point C. So the lateral loads associated with the hinging of these two, point B and point C, is just equal to 2 times MOY divided by H. You come up with 355 kPa of earthquake loads. And then that earthquake loads times the H prime, which is the superstructure mass center to the top of our pile cap, and then times E times H prime divided by B, 36 kPa here, and you can get a delta P, the actual load level change. So the one column will be in compression, one column will be in tensions, and then the P load in the column becomes, in the compression column becomes 750 plus 276, you get 1026, and the actual load in the tension column becomes 750 minus 276 equal to 474. And you do the moment curvature analysis with these two actual load level again, and you come up with this new set of moment curvature properties, phi y, phi u, my, and mu. Now you use the effective stiffness of average of the two columns here, come up with your EI effective for your bend, and then plastic hinge length is calculated here equal to 32.2 inches. Now let's do a pushover analysis. For the event 1, no hinge has occurred, so the whole bend is in elastic phase. The plastic MP of the point B at point B is 3319 kPa, and at the compression column is 3779 kPa. Now, if you put a one unit cape load here and draw on the moment diagrams of your bend, you got a 10 kPa here and 10 kPa here, so that you know, in order to achieve this plastic moment of at point B, you basically need you need that number 3319 divided by 10, and you get your E1, which is 332 kPa. With that 332 kPa, the point B is going to achieve the plastic hinge, and the point C is still inelastic. So this is event 1, and then you can calculate the displacement of your bend based on the elastic stiffness, because for event 1 is elastic stiffness. And now here we've got two columns in elastic range, and the stiffness of that bend is 6 times EI. 6 times EI effective divided by H cubic. And you can calculate delta 1 correspondingly using the E1 times the divided by the stiffness, which gave about 2 inches of deflection, lateral displacement here. Now then the next step, you go to the event 2. At event 2, the joint, the top of column at point B has already reached the plastic rotation, has already reached the plastic moment. So it's going to be a plastic hinge here, and you have only one column which is able to resist the lateral loads. And remember, on event 1, you already taken away from 3779 kPa, you already taken away 3319 kPa. You're left with 460 kPa here. So the reserve capacity at point C is 460 kPa. With that unit nodes, and do unit node again, and put one kip here, and draw your moment diagram. Figure out your moment diagram here. In this case, because you have only one column which is capable of resisting lateral loads, so the moment diagram, the moment at the top of column here is 20 kPa. So in order to make that 460 kPa disappear, you need 460 kPa divided by 20. You need 23 kPa to let the point C to reach plastic MP. So the event 2 is basically equal to E2 associated with event 2 is equal to 23 kPa. And then you calculate the stiffness, the elastic displacement, lateral displacement for this event 2 again. And this time, you only have one column effectively resisting the lateral loads, so your stiffness drops down to 3 EI effective divided by H cubic. And you calculate that again, you get 0.28 inches. Now, this after this event 2, both of this column, both B and C has reached the plastic MP. So the bend has formed a mechanism, and it can collapse, but it can still rotate. It can still go because the plastic rotation capacity of the B and C has not been achieved. So for event C, you just let the whole system, let the mechanism moved delta 3, and calculate the angle formed by the pier cap and the column, and see if that angle reaches the plastic rotational capacity of the hinge. And so here the calculations should say for point B, the plastic rotational capacity is equal to 4.95%, and point C you got a 4.02%. And this is for compression column. For compression column, there's a less rotational capacity, and in tension column there's a more rotational capacity. And even take away the rotation that already occurred in at the tension column during event 2, the compression column still reaches the rotational capacity first. So the controlling case is for the compression column to reach the plastic rotational capacity. And you follow that calculation, you get delta 3 is equal to sigma PC. I'm sorry, sigma PC times the length of this column here, height of this column, you get that delta, which is 9.65 inches. So then you add up all your lateral loads resistance coming from event 1, event 2, and event 3 together, and then you got your total lateral capacity of your bend, and then you get delta is equal to this number here, 11.95, and the yielding displacement is equal to 2.02, and so this bend has a ductility capacity delta U over delta Y is equal to 5.9. So this is pretty high. And here is the calculated pushover curves. The first straight line, the elastic response line, is event 1, and at the event 2, you got one column gets into plastic hinge, one column being plastic hinged, and so you got one column still inelastic, so you got less stiffness. So this here is the event 2, and then on the event 3, you just have a mechanism. You can achieve zero resistance coming from your displacement, so you have a plastic flow over there for event 3. Now for the design category B and C, you don't have to do this pushover analysis. The code gave you an implicit displacement capacity calculation, which is given. This is an empirical equation that you can follow to get those. Now let's go for the foundation modeling. Foundation modeling. We have a spray foot. The common foundation type is spray footing, pile supported cap footings, and drill shaft. The actual requirements for the foundation modeling is for the seismic design category B and C. You can use modeling method 1, which pretty much model the foundation as rigid. For design category D, you definitely need to go to modeling method 2. Also for seismic design category B and C located in the site class E and F, you also need to use a modeling method 2. Modeling method 2 requires you to consider the foundation flexibility when you have the displacement contributed by the foundation flexibility accounts for more than 20% of your total pure displacement, then you need to consider foundation flexibility. Regarding to the foundation flexibility calculations, there's a couple of ways, and what the code recommends for the spread footings, just use the FEMA 273 method, use the best estimate string compatibility shear modulus G, and then vary the shear modulus G up and down 25%. For pile foundations, obviously there's a geotechnic expert needs to tell me, but once you get the pile actual stiffness for single piles, you can always integrate them, as you're shown here. And for drill shaft foundation, usually is using the estimate point of fixed. For abutment modeling is actually difficult. And this figure here conceptually showing the stiffness property of the abutment. So at the pull directions, it's just going to be the stiffness coming from the pile. And at the push directions, before you close the expansion joint gap, you're only going to get the stiffness coming from the pile. But once that gap is closed, and the girder has been pushing on the backhauls, and the backhaul is pushing on the backfill behind the backhauls, and you get the passive soil resistance, and your stiffness come up significantly. But the passive soil resistance can fail at a certain displacement. Once you pass that point, it becomes a pile stiffness again. So abutment stiffness modeling is pretty difficult. And then for the modeling of variance, and this is actually a very controversial subject. For modeling your variance, the first question you need to answer is whether your bridge is intended to be designed as seismic isolated. For bridge which is intended to be designed as seismic isolated, in the AASHTO code, AASHTO guide spec classify that as a type 2 structures, means your superstructure and substructure remains elastic, and the only ductile elements in your system is the bearing. So for seismic isolated bearings, you keep all your other structural elements elastic, and just model the bearing as a ductile elements. And you can get a property from the manufacturing for this isolated bearings. And if you do not intend to design your bridge as a seismic isolated, then the bearing should remain elastic, and that means you need to protect your bearing to make sure that the bearing does not fail before your ductile element fails. So you basically need to protect your bearings for non-isolated seismic, non-isolated bridge. And then let's talk about the concept of displacement-based seismic design. Traditionally, based on we're using force-based design. So you basically run your response spectral analysis and get your elastic analysis, and divide your force reading out from your elastic response spectral analysis. For example, the base shear, the overturning moment, read out from your model, and then you divide that by your response modification factors, the R factor here. And the logic behind this is that, as you see in this figure here, we got a delta and we got an earthquake force, and the inelastic response and elastic response, and the delta y and delta u. So this angle and this angle, they are two similar angles. So your design load is going to be EP, and EP divided by EE is just equal to delta y divided by delta u. Which is also equal to R divided by 1. So the response modification factors R represents the ductility capacity of your earthquake resistant system. If you have a ductile system, ductile substructures, you're going to get more larger R. If you have a less ductile, for example, a pier O, you're going to get less R. If you have for multi-column bent, is more ductiles, you get a larger R. However, the problem associated with this force-based design is that the code gives you a constant R. The problem associated with the constant R is that it does not differentiate the magnitude of earthquake. As you can see from this figure here, as your earthquake magnitude get larger, your elastic response get larger. You're going to get an R2 number here, and for a small scale earthquake, you're going to get an R1 number here, and the R1 obviously is less than R2. So intuitively, this means for a small scale earthquake, you don't have much post-yielding displacement. For a larger earthquake, you get a lot of post-yielding displacement. So correspondingly, you can reduce your force more in a larger earthquake. And for a small scale earthquake, you cannot reduce that much. So when you have a constant R and you use your elastic response and divide by this R, sometimes it creates confusion. So the displacement-based design, get rid of the R. Here you explicitly calculate your displacement capacity, which is given by this purple curve here. And then you run your elastic analysis to get your displacement, elastic displacement, and the actual guide specification used equal displacement assumptions. That assumption written as displacement resulting from inelastic response is approximately equal to displacement obtained from linear elastic response spectral analysis. So what you design load is simply the inelastic response, the plastic hinging moment, EP. And what you need to check is this delta D demand displacement is less than the displacement capacity delta U here. So comparison with two design approach, the traditional force-based design is accommodated by the Ashton LRFD bridge design specification right now, and for the displacement-based design is accommodated by Ashton guide specification for LRFD seismic bridge design. Both methods require you to finish the strength and service limit state check first, and then go ahead with your seismic design. Well, I'm out of time here, but I'm going For displacement-based design, there's a concept of capacity protections. Capacity protection basically means in your system, you want to concentrate your damage into your ductile members. So you need to make sure the member that are connected to the ductile members, which you intend them to be elastic, they need to be capacity protected. So they will remain elastic during during the inelastic earthquake response. Those capacity protect member includes column shear. You need to make sure your column shear capacity exceeds the overstrength capacity of your flexure strength of your column. Pier cap, foundation, and joint. All those are the capacity protect member you need to design to equal or exceed the overstrength capacity of the ductile members. Let's see some examples here. I'm out of time, so I'm going to go quickly. So this is a 3-span steel girder bridge. The model is showing up here, and this bridge I did a prototype model, so it's an exact member-to-member modeling. It's supported by a 3-column bent and a 2 integral component. Now, the transverse mode, the major mode of this eigenvalue analysis is shown here. This is mode 1. This is the transverse mode. And then the second major mode is the torsional mode. And then the third mode is the longitudinal mode. Those 3 major modes constitute majority of the mass, so I do not even need to consider any more nodes, just use those 3. And then this is the plot from the model for the Pier 1 displacement demand, which consider the 30% of EX plus 100% of EY as transfer directions. As you can see here, I got a 1.5 inches deflection at the pile cap level. I got 4.2 inches of deflection at the pier cap level. So the relative displacement of the column is about 2.6 inches. And this blue curve here is the pushover curve calculated based on event scaling. This red curve here is the demand displacement curve coming from the response spectrum analysis. As you can see, there's a plenty of reserve of ductility for this bend, so the bridge is okay. And the next example is a 4-span concrete box girder bridge. This bridge is supported on an alternate pile cap. So the pile cap and the pile is also modeled as a structural element. And this is the transverse mode. And then this is the longitudinal mode. Oops. Where's the torsional mode? Yeah, this is the torsional mode. This is the torsional mode. So the three major mode constitute majority of the mass, and that's the 3 major mode. And the displacement plot from the Pier 1 is 17.75 inches at the top of column and 10 inches at the bottom of column at the pile cap level. So the foundation is pretty flexible. The relative displacement for this column is about 7 inches, 7.5 inches. And the pushover curve of this column, because this is a pretty simple calculation for the pushover curve, it's just 1 inch and it's done. The blue curve here shows the pushover curve, and the red curve here is showing the displacement demand. So this column barely yields. As you can see, it's just exceed the MP by a little bit. So this column barely yields. And if you do, that means what you have in your model, the force in your model, the elastic force is going to be your design forces. All right, that's my presentations. Thank you very much. Oh yeah.
Thank you, Ling. All right, thank you, Ling, and thanks everyone for attending the session. As I mentioned in the beginning, we have follow-up sessions on this course. Gonna be 2 more courses. One is in-depth case studies and discussion, which is gonna be on March 22nd. And we have numerical modeling and showing how to do this seismic analysis and seismic design and response spectrum analysis with Midas Civil. It's gonna be on April 2nd. And also we have 2 more sessions are coming up. One is a technical seminar, which is on March 28th, is on the curved steel eye girder bridges. And then there is one follow-up session, which is going to be tomorrow, is in-depth discussion, which is follow-up session for the last week seminar that we have is on the displacement time history. So please join us in these sessions, and we can discuss more in details in these upcoming courses. And you can find more information about the upcoming session, and also you can find the recorded webinars and go to goodengineers.com. So please go to goodengineers.com and you can find all the information there. And if you have any questions, please feel free to contact us at midasoft@midasuser.com. Thank you so much, and everyone have a good evening.